It is a very great pleasure being here this morning with such a great distinguished audience, Mr. Michel and everybody. This is going to be a lot of fun today. And one of the things that I like about this topic, and I think some of the members of the audience will appreciate this, particularly Professor Hussein, and that is that when you look at wind energy, this is, I'm going to prove today that this is one of the major issues and critical, but that turbulence is a first-order problem in this. And basically what I'm going to do today is to target on the issue, let me see how on the issue of the wind farms and the performance. So if you look at the graph in the left-hand side, that's a chart shown by DOE in 2008, and the idea was the goal is to reach 20% of wind energy by 2030. And I will base a lot of my discussion based on that goal. And then the other aspect of this, as you see on the other side, is a professor, is one of my colleagues, Andy Swift, and you will see that there would be a great value of educating the future workforce as we try to reach the 2030 goal. The other aspect of this, you will see a natural catastrophe. As we begin to deploy many of these big wind farms, particularly in the coast areas, you may need to worry about wind hazard mitigation of those infrastructure. So if you look at the other one, this is a very famous picture that anybody in the wind community and doing research will see that this is an offshore in Denmark. And you could see this is a beautiful visualization of the interaction, of the wake-to-wake interaction of a deep wind farm. And this is very important because it's that wake interaction between the flow field and the turbulence will affect the performance of the wind farms. The last in the right-hand side shows a new paradigm that we researchers and people in industry must adopt. And that is basically most of these blades are designed from the perspective of optimizing a single blade and at most to optimize one single turbine. What we propose here is an integrative approach where it has to be considered as a holistic approach where the blade design is not of a single turbine but of the entire wind farm. So this is quite exciting from that perspective, and this is what will base the entire discussion. Now, if we go back to this picture, you will see immediately that the first turbine, most of the turbines are designed for a beautiful incoming flow. You could see, I'm trying to find the, you could see that this will be a nice laminar flow at the beginning. As the flow reaches the first turbine, goes to the subsequent turbines, what you see is a turbulent flow. In fact, what you see is a boundary layer and a spectrum of scales that are interacting with the turbines behind. What does that mean? It means the following. If you fly in the airplane, when the air pilot is saying we're going to have a lot of turbulence, everybody gets scared. This is what these turbines are experiencing every single day for 20 years. So they have external loads, and those loads are induced basically by the wake effect of the turbulence. So this is a very, very important problem that limit wind farm performance. Now, it's even more than that. If you look at one of the questions, this is one of the challenges that the community and Dick mentioned that in some point, is the capacity factor. In other words, when you build a big, large array, what you have is the ratio of the energy that this one farm is producing over the amount that is rated. And what you want to be able to do is to increase that. The more you increase that value, you know what that means? More profit these wind developers will make. And that is the whole foundation of why we need to have some fundamental research in this. Now, there's one issue here, and that is the issue of uncertainty, right? Because the wind is not blowing all the time consistently. If you have a complex topography, then the interaction of the flow field with that region becomes more difficult. That means that we need to mitigate those uncertainties. Why? Banks do not like uncertainties. And I will explain you toward the end why it's so important to reduce that uncertainty. If you look here, these wind turbines are operating very nicely, very beautiful. Over time, you would find that those blades become rough, not because of the combustion as something like happening in gas turbines, but because of mosquitoes. So you begin to increase the drag, and that means it was shown in 2001 that these produces losses of 25%. Bad news. If you try to put those wind turbines in Minnesota, Wisconsin, very cold areas, then you have an issue that is very common in aerospace industry, that is icing. That is bad news too. And so all of this issue has to be considered, and all of them will contribute to the wind farm on the performance. Now, let me show you this graph here. This is a graph, a very, very famous picture by Rebecca Bertelmi, and what she showed here is a normalized power. So it's the power of the first turbine by the incoming flow. And then on the bottom, you see the number of turbines. So if you look at the offshore wind farm that I have at the bottom, what you see here is the separation distance between the turbines make a huge difference. And that separation distance is critical because it's the interaction of the wake to wake of the entire rows. Now, it's more than that. You could see that when they're separated only 7 diameters from each other, you have a power drop of about 40%. This is not good news. So you could have a wind farm that is operating at low speed and performing very bad because of some issues like this. Okay? Or you could have very good wind, but this wake interaction will really make a nightmare for most people. Now, if you look at this problem, and remember I was trying to tell you, can we look at this problem from more of a system analysis? In other words, if I can have very good information about what is the velocity profile of the velocity, turbulence, everything, I can then, I can then know what the inlet velocity is, I know what the outlet is, I can use this in models to create optimization. Okay, because we could optimize the cost of energy, or we could optimize the power generation for the entire system. The answer to that, instead of having a particular layout, is simply implied that you may have to change the layout. And we did that. We actually did a wind tunnel experiment. I don't have it here. We actually did a wind tunnel experiment in which we basically took an array, scaled down, and we were able to increase the capacity factor by 6%. Now, just to give you an example, what is the numbers that we're talking here? If you take a system that you increase the capacity factor by 6.4%, like in the case we did, you're basically talking about that if you build 10 wind farms, and each of them are 200 megawatts, in 20 years, you're making an extra profit of $1.1 billion, okay? And this is a big deal. And this is simply in a case where we're basically saying we need to integrate science with what's really happening in the field. If you could improve that factor by 25%, you're talking about $3.2 billion additional. So this is a very, very important issue, and something that we're actually doing. In fact, that work that I show you here, that was done in a paper with, that I co-authored with my colleague Achille Mesak and one of our students. If you go further here, this is the point that I'm talking about. We cannot approach the problem of wind energy from a simplistic approach of looking at a single blade or even a single turbine. It has to be the aerodynamics of the entire layout. And this is where I believe the major changes. This is what we call system of system approach. Now let's show you this. So to reach that goal of the 2030, and there's more in motivation. In fact, I appreciate the question that the lady in the second row asked about the water issue in many of these other sources of energy. And this is something that normally we do not address as we should. We know we're doing wind and we're doing renewable because of the footprint of CO2 in the atmosphere. Good, that's well known and people would know that. But in terms of the water resources, we're talking about that to reach the 2030 goals, we're conserving about 4 trillion gallons of water, okay? This is a big deal. In the long run, we will not be fighting about oil. We'll be fighting about water. And I think that this is one of the major motivations why one should be looking at wind energy, in particularly, as the sources of energy that would solve this problem. And you're looking at, to reach the 2030 goal of 20%, you're talking about we have to deploy 275 gigawatts of energy. That translates to $550 billion. Good business, there's good opportunities for everybody here. Now, in terms of to go to that level, it means this. It's big because they will be creating jobs, you will create new jobs, there will be innovation, there will be opportunity for educating the future workforce, okay, just not a big deal. There will be issues with national security, but it will also have an impact in preserving natural resources. Now, I will point this out very quickly in terms of the jobs that you could create, but I'm gonna move about that, okay? But in terms of the research and the importance of this wake interaction, you can see that this is one of the measurements that one of my colleagues, John Schroeder, did at Texas Tech, in which he was able to measure the wake, and he was able to show how far this wake extend downstream. So you see these wakes in these turbines, and this is highlighted in blue, it's actually convected down very far downstream. So this is a very important issue that contributes to the wind farms and the performance. Now, if you look at some of the other experiments, this is one of my collaborators in Johns Hopkins. He performed numerical simulations of this problem, and he was able to show also that this wake interaction, when you see in blue, that's where the turbines are. And the blue, all of that is the propagation of the wake. So you can see when you look from the top, there's a big effect of the wake. So this means that there's a big opportunity for people doing turbulence and doing simulations to be able to contribute to this problem. Something that I did not mention, if you look at the picture at the bottom, you see a wind turbine on the floor. And this is actually a consequence of the external loadings on the turbines. So again, you see that, that this is a very important issue. This is one in which we try to use wind tunnel measurements to improve the optimization of those layouts. So there's a great potential here to make a very, very big impact, but the one that makes a lot of sense from the point of view of the job creation is that in terms of education, we could estimate that there's about 12 to 17% new jobs or training opportunity in the academic. So this is a good market that new jobs will be generated, but there's one point that I want to make. And can we do this? The answer is yes. And I would make this, we need a serious commitment. What I mean serious commitment is investment. And one part of the investment that is a problem, the banks. Because the banks, they don't like the uncertainties. They want to reduce uncertainties, right? So new technologies could not be deployed. That's a major problem. So you have a field that needs a lot of new technologies that has been developed but could not be implemented because they have not been tested, right? So we need sites that could test those projects, but we need investors that will not need bank financing to be able to implement this technology. So these technologies, this new research will really make a big impact in the economy, the research, and in the country. At the same time, water, we're protecting our natural resources. So I think I'm done. Thank you so much.